We're
You're
going to take a step
doing
back. Module 11, yes.
module
The quantum numbers and electron configuration. So let me quickly share my screen here. So who can tell me what they remember from electron configuration?
Which module are we doing?
Module 11 now with quantum numbers and electron configuration. So going back to that module, like who can remember like what is electron configuration? Like why do we use it? Or more specifically, how is it used?
Let's just see where they're like located.
Yeah.
Yeah, exactly. So, and the way we would do that, because remember, electrons are packed in shells or in orbitals, right? So if we were to look at a periodic table, so like here's like a really bad drawn periodic table, where each row is an energy level. So it's also like a subshell. You have like 1, 2, 3, 4, and so on. So who can remember what's the first shell, like from the groups 1 and 2 technically, and this little one up here, helium. But don't worry about that. Like, what's the first type of shell we work with from the ground up? Yeah, the s orbital. So we have s, and how many electrons can that hold up to a maximum?
2.
It can hold up to 2 electrons, right? And how much? What's next though? We have the p orbital, and how many can that hold?
6.
And what comes after the p orbitals?
D.
D, and how many can it
F.
hold? And then after that?
F.
And how many can it hold? Yeah, 14. Typically, you won't be working with f orbitals, but it's good to know. It's good to know. So if these electrons can hold that amount, remember that electrons like to be in pairs. So for your s orbitals, you would have like one box. So you have one electron and then another to make a pair. So that it would take 2 electrons to fill it up. Your p's, again, you would have 3 pairs in order to fill up all of it. Your d's, you would have.
Wait, because I know it's like we have like to solve it, but can you say the name of what that is called? Because that kind of based on the theory part.
It's the orbital or the shell or the ring. Usually more than usual you'll call the. Do you mean the boxes?
Yeah.
Is this just the electron box diagram?
Yeah.
It's the orbital box diagram.
That one.
Or OBD for short. I like to call them OBDs most.
So let's take an example of how we can find electron configuration. So let's do carbon. So looking at where carbon is positioned on the periodic table, how many electrons would it have at first, like looking at it?
I think it has 6. I don't know.
Yep, because remember, the number of protons it has is the same to the number of electrons in its ground state, which is the version you see on the periodic table. So we know this has 6 electrons, right? And what position is carbon in terms of orbitals?
P.
It's in P, right? But which P?
2. 3?
Like which number?
2.
Yeah, it's in the 2p orbital. So we know that's where it lands, so that means that's the highest orbital it can go to. So let's start from the ground up with, since we know it has all orbitals before it. We know it has the 1s, 2s, and then so we've reached up to its maximum. So now we got to fill up the boxes with 6 electrons, since that's how much it has. So how would I start filling up my 1s orbital?
You fill up the up first, I guess. Then down, I guess.
All right. So now that's filled, we can move on to the next box or orbital. So how do I fill up my 2s orbital?
Well, it's filled up, so it's up and down too.
So we have 4 electrons in total now, so we're left with 2. So how do I fill up my 2p orbital now?
So it's going to be up and up for the like first box, second box, yeah.
And is that it? Have we used all of our electrons?
Yes.
So we've gotten to this point, right? So to write out the electron configuration, we would have like the elements, right? Or we have like 1s and then the number of electrons, which is 2. 2s, the number of electrons, which is 2 as its exponent. And in 2p, we have 2 electrons there, so it'd be 2p2. So the electron configuration for carbon would be 1s2, 2s2, 2p2. But there's a shorthand way of doing this. And what would that be? What would that be called?
I don't know the name of it, but are you talking about picking the noble gas before that?
Yes, exactly. And it's called the noble gas configuration. It would typically call it like that. because remember, if you look back at the periodic table, if you were to follow back, you would notice that a certain, like somewhere along the line in your configuration, it's the same as a noble gas before, because noble gases they have a complete shell. So they're like the reference. They're the reference that elements look up to. In this case, what is a carbon's noble gas before it?
Helium?
Like helium. So what you would do, you write brackets, the symbol of the noble gas, and the configuration that comes after it. So in this case, helium is
2s2 and 2p6.
yeah. Since right here, helium is 1s2, 2s2. We basically replace the configuration of helium or the noble gas, and then write the configuration that comes after for this specific element. So both of these ways are correct. It's just sometimes
Alan,
once you start, oh yes,
actually for helium, it's only 1s2.
1s2. Oh, that's right. My bad. Yeah. Thank you for correcting me on that. Yeah. I believe someone else corrected me on that. I just couldn't hear it. Yeah, so it'd be like this. Yes, thank you for correcting me. So both of these methods are correct. It's just sometimes easier to do the noble gas method when you do a bigger atom. So let's do that, for example. Let's go with sulfur, right? Actually, no, let's go with bromine right here, Br. So first of all, what position is bromine in terms of the orbitals? Like what orbital is it in? Oh, did someone say it or? So remember, look at your periodic table, because you remember that the first two groups, that's like your S, and then the middle block is your Ds.
4p.
Yes, it's in the 4p. Because remember, it's on the 4th energy level, and it's in the p block. So the final orbital has to be a 4p, right? And how many electrons does it have?
5.
No, I mean, like, how many electrons does bromine have in total?
35.
35, right? So we need to use all these 35 electrons. So let's start off from the ground up, starting with S. We know it has, so it has our 1s, 2s, 2p, and then, our 3s. And then, so what do I do from here, 3s? Do I go straight to 3p?
Yeah, 3. Yeah.
Sorry, can you repeat that?
Yeah. 3p6.
Yes. Oh, sorry, I haven't got that point yet. Sorry. So yes, it'd be 3p. So you're saying 3p6, yes, because previous shells will be filled, right? So we go from 3p to 4s, but then from
3d10 or 3d.
So yeah, we'll have 3d, and yes, you're right, it's 3d10 because previous shells will be filled up, but we'll just leave them blank for now so we can count our electrons. Then we will go to 4p. So from here, since we know, let's just count up our electrons first, since you're right how we fill them up, starting with the up arrows and then pairing them. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and then 30, forgot the rest here. 31, 32, 33, 34, and then 35. So we have all this filled up. So what would be its configuration the long way?
Like you mean 1s2 to 2s2, 2p6, all that?
Yes, exactly.
Oh.
So yes, you were 1s2, 2s2, 2p6.
2p6, 3s2, 3p6, 4s2, 3d10, and 4p5.
Exactly right. And what would be its noble gas configuration? Because this is a lot to write down when you have like a limited time. Excuse me, when you have like limited time during your exam.
Argon.
It would be argon.
Yes.
Argon.
So we will have our brackets argon, and then what would come after argon?
One is 4s2.
So we have 4s2. So anything after our, where is it here? Well, yes, anything after our 3p6, because that is the configuration for argon. So we have 4s2, 3d10, and then 4p5. Now, remember that your Ds are a level lower than the energy level they're on. So sometimes to make it like follow the pattern from low energy level to highest, you can write it as bringing the Ds first. So it'd be like 3D10, then 4S2, because it is a lower energy level. Like the other way is fine, but this way it's more concise. Like it follows that pattern.
That was supposed to be 4, supposed to be at the end, but I don't know.
Sorry, can you repeat that?
The 4 is supposed to be at the end. Does that only happen with the exceptions?
Not well, yeah, because we'll cover the exceptions right now. But for now, this would be its electron configuration for bromine. So you guys got the hang of it. But yeah, so let's cover the exceptions right now. So one of the bigger ones would be copper, right? So Cu. So who can tell me the configuration for, well, who can tell me where copper lies right now? We'll use its abbreviation using argon. And we know so what comes after that argon for?
First 2 and 3D9.
So in this case, the reason it's an exception, if you remember, that shells like to be either half full or completely full in order to be satisfied if they can help it. Since the 3D is in a lower, so our 3D is at a lower energy level than our 4S. Let me fix that. Really wants that electron, right? So let me quickly fill this up the way it is. Since it's really looking for that electron to be filled, and since orbitals can be half full and be satisfied, what it'll do, it'll take the electron from the 4s and bring it down. So now, even though 4s got an electron taken away, it's still satisfied because it's at a half shell. So because this is the most stable it can be, so the actual configuration would then be 4s1 3d10, because this is a more stable configuration, because because it's so close to being full that it could just take away from the S and leave it satisfied with half. Does that make sense?
Yeah. Are we gonna do it like that, or do we do it like the 3D10 and 4S1?
You could do 3D10 4S1. That is also correct. Okay. I just did it like this because trying to show it.
Yeah, usually the way that you write it is you go lowest energy to highest energy level, and by energy level I mean the coefficient or the number in front of the letter. So it would be like 3 and then 4, but you know, we're being lazy because erasing. So yeah.
So just keep that in mind. Do you guys have any questions so far? Anything you guys may be confused on right now regarding electron configuration? Let's see.
So let's say that we were to do like another one, like chlorine or something like that. For this case, you know how it's
you mean chlorine or
let's
chloride?
talk about bromine again because it has the D shell.
So do you mean bromine or bromide? Because remember your suffixes, how you say it depends, because bromide is the ion and bromine is the atom.
Well, let's go with bromine.
All right.
For that one, you know how we had like the D shell and everything. For this one, does the 4S goes before the P?
Yes, it does, because if you look at periodic table like the same way, it goes from S to P.
So in this case, it will be D10, 4S2, then 4P5, right?
Exactly.
Okay, that makes sense. Right. Except in exceptions.
Well, exceptions can also be because remember copper, it was it could be like it was like 3D10 4S1. It can also be like this because remember you go from lowest energy level to highest.
Yeah, but we don't have to worry about the P and the exceptions, so that's fine.
Yeah. Well, except
halogens, but yeah.
Yeah. Well, halogens are just there. Like if you look at what's in the d orbital, You notice that copper doesn't really have any p's, does it?
Yeah, that's fine.
Well,
Like,
before it, but I mean like in its final shell. Because right here, this is like the final shell we're kind of focusing on, or more specifically, this. Does that help like clear up your
yeah,
confusion?
yeah.
Perfect. So does anyone else have any questions, anything they're confused about in terms of electron configuration?
You know the last example you gave for copper?
Yes.
What we're trying to do is make the last shell more stable, right? No,
Yes.
always the last one.
The one before the d orbital specifically, because if it can help it, it'll try to be either full or half.
Okay, cool, thank you.
You're welcome. So if are there any other questions that anyone may have?
Well, I do have one actually. It's related to the same thing. When let's say he asked for copper, do we do this one? Do we do the exception, or we don't
Yeah.
count it?
Yes, you do, because copper is the exception, because
Okay.
you need to write the most stable the stable configuration, which is, let me rewrite it, which is the argon 3d10 4s1.
Yeah, because sometimes they give us like copper 2 and stuff like that.
Well, let's work with those, because those are like ions, right? So we have copper 2, which is 2+, right? So when it gets positive, what does that mean?
It's losing 2 electrons.
So if it lost 2, so if you're looking at it in ground, like let's look back at ground state, right?
It would
Where it
consider
was
like cobalt technically.
it would be considered as cobalt. So what would its electron configuration be?
No, going from argon, it should be 4s2 and 1, 2, 3. D6.
So 3d6. So I'm not gonna. D is supposed to go first. I'm too late. We're
Yeah.
like kind of short on time. So here, I believe you did get a problem like this in your workbook, where it is trying to be as stable as possible. So what I believe does happen, Jeremiah, Sophia, correct me if I'm wrong, is that it does want to try and reach that full stability, because technically you could have empty orbitals. So what it does, it'll pull the electrons from the 4s, because it can either be full, half, and even empty, because you could just be, it has to be like one of those 3 satisfactions. So it'll pull away those electrons, and then we will get 4s0 and then 3d8, because it's trying to be as stable as possible.
Yes, except when you are making these ions, it's always a good idea to do the neutral configuration first. So the way that Alan has it up here, this one, that's the correct one that we said for stable neutral copper, right? So when we're making our copper 2+, we said we're losing 2 electrons, so we're actually going to take it away from this configuration. So this is going to be 4s0, and this is going to be 3d9. Because if we try to go off of the periodic table, we're going to be missing an electron. So that we need to do our ions. We're going to base them off of our correct electron configuration for our neutral atom. Does that make sense?
And you always start with the highest energy level, like they were saying earlier.
Yeah, because when you're taking hopefully you're not a psychopath, but when you're eating pizza, you don't eat the pizza like what you would call it? I don't know, crust to wait, that's a bad analogy.
From the crust, right? You don't start from the crust.
When you're cutting a cake, right? You're not a psychopath. You're not gonna cut your slice from the middle of the cake and go from there, right? You're gonna cut it out from the outside and then work your way in, right? So it's the same thing with the electrons. Hopefully you're not a psychopath and you eat your cake backwards. But if you do, that's not anyway. So you want to take your electrons from the outer shell first before you start moving towards the nucleus. Does that make sense?
Okay. Maybe a little visual example might be able to help.
Yeah, go for it.
1, 2, 3, 4. Okay, so I like to kind of draw. For my students, I usually like to draw the whole atomic structure, so that it'll be a little bit more visual. I'm a visual learner myself, so it helps me a lot to do visuals. So 2, 8, this is the second. 1, 2, 3, 4, 5, 6, 7, 8. So that's up to 3p6, right? 3s2, 3p6. Then you start filling out the 4s2, right? So I'm gonna put it in a different color so it's a little bit more visible. So this is the so these green ones are the 4s, right? So remember the d orbitals are filling up on the third shell. So that's why they have a lower energy, because they're starting to fill up the previous shell. After you filled up the 4s, you start filling up the third shell with the d electrons. So up to this point, so if you're filling out for copper, you would think you would have 4s2 and 3d9 because of how you would normally fill out electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it wants to be full. And another way I like to show that is because of the orbital box diagrams. So you have 4s, your 4s, then you have your 3d electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see that empty space right there where there could be another electron? Okay, so the d electrons have this tendency of wanting to be either full or half full. So if they want to be either full or half full, so meaning they want 5 electrons or 10 electrons in their d shell, where are they going to take that s electron from? All right, you guys already know the answer, but let's see if you guys paid attention. If they want to be full or half full, where are they going to take that extra electron from?
From the 4s?
From the 4s. Yes, Elizabeth. That's my student right there. Proud. We stand. Right. So we're going to take this electron back down to the d. So we take this away. And then we're left with, that's why we're left with 4s1, 3d, 9. And over here, we take out one of these electrons. Oops. We take out one of the outer shell electrons. No more. And it's no more. And now we put it over here. We have a full third shell. We only have one electron on the outside, which then we can just pluck out when we turn this into ions, right? Does that make sense? Does the visual example help you guys? Of course, this is just what you guys already talked about. So I just wanted to do a visual example because I noticed there was.
So like, are there any questions right now regarding like why it is that way, or anything you guys may still be confused on?
I think we're all good.
All right.
Right.
So-
So sorry.
No, go ahead.
Yeah. So just to recap, this is the exceptions are in the d orbitals. I think there are exceptions in the f orbitals, but we don't deal with that in Gen Chem. In d orbitals, we have exceptions because they want to be full or half full, and these exceptions are almost always very, very one electron away from being half full. And in the case of palladium, it's 2 electrons away from being full. Palladium is a little bit weird among the exceptions because it actually takes both of the s electrons and it fills up its whole shell. But that's palladium. That's for palladium. But for the rest of them, like for example, we already saw about copper. What other exceptions can you guys remember?
And copper, silver, gold.
Copper, silver, gold. So
Then
silver
it's
is
chromium, MO, I don't know, and tungsten.
molybdenum, and tungsten, right? So for example, silver is basically the same thing as copper. It's missing one more electron, so it's going to take that from the s orbital. And for example, chromium, how many electrons does chromium have? What would be the shorthand configuration for chromium?
argon, 4s2, and 4, 3d4.
Yeah, you guys would think that, right? That it's 3d4, but so let's draw it in the orbital box diagrams. So we have 4s2, 3d4. So again, what did we mention that exceptions are special for?
Taking electrons
They take electrons because?
to be half full or full.
Exactly, right? So chromium is an exception because it's going to take?
1 electron from the 4s2.
Right. So it takes this one, takes it over here, and we have, voila, a full shell. A half full shell, my bad. Because they're more stable. Full shells or half full shells are more stable. So the d electrons, we're gonna the d subshells want to be either half full or full. That's why the exceptions are gonna take away an extra electron so that they can be full. Okay. Does anybody have any questions, concerns, complaints?
It's kind of a little off topic, but which one are we gonna see on the exam? Honestly,
Honestly, we don't we don't know.
there's like technically 3 ways I saw it right now, which is the basic one, which you just leave it like that without the exception. The one that I don't know. I just.
Oh, you mean to choose the right answer if it's an exception?
It's because it's like when the exam, basically you guys did like another one I didn't know about, and on the exam, technically I only saw the one that I knew, and it was just taking. Never mind, but that's just weird the way this is gonna be. Honestly,
Are you talking like the 1s2, 2s2?
Yeah, it's just like on the exam once you like do them, and especially when it's copper or like the +2, it's weird.
How do you know what the exceptions are?
The exceptions are always going to be transition metals. Yes.
They're always in the d orbitals. So if it helps you guys, it's mostly the ones that are in chromium's group. So chromium, molybdenum, tungsten,
and then copper's group.
The copper's group, and then
Does anybody
silver.
have a periodic table to pull up?
Oh, I think
I could put mine up.
Oh,
to the
put up
screen.
one. Oh, put up yours because it's your screen.
Oh, this, yeah. If I can. Well, no, I was gonna say it up to the camera, but.
Oh no! Pull it up on the screen.
Oh, yeah. If I can look for. Hold on. Periodic table. Oops, sorry about that. Let's see.
Oh yeah. When I was saying like the copper one, you guys already like took both of the 4S, right? And like from what I knew, I thought was you just supposed to like just do it how it asked you. I didn't know you're supposed to add the exception to it.
Oh yeah, no, that's why we're going over that, right? Because yeah, you could do it the way that you that you're taught, right? But we're telling you that's not the most correct way because it's not as stable as if you were to pull in an electron. So the correct answer is the way that you write it with the exception. So it wouldn't be for 3D9 4S2, it would be 3D10 4S1.
Right, so here's as best I can really pull it up. So like if you were to like look for your, typically these are the exceptions. Oh, let's see, the chat's blowing up. Okay, so let me get this here. So typically it would be in this group for our chromiums. So usually this group, and then our coppers, those would typically be our exceptions because they want to be either half full or completely full. So they would take from the RS or RS orbitals, which are like right here. Let's see. Are there any questions? Anything anyone else confused about? I'll take that silence as a no. So if we move back. So let's move on to the next topic of why electron configuration is important, which is now quantum numbers. So who can tell me what are the 4 sets of quantum numbers, like just like by their letter?
Wait, what?
Like what are the, who can tell me like what are the 4 quantum numbers that come in like a set?
Quantum.
N, L, M sub L, M sub S.
Exactly. M, L, M sub L,
Yeah.
and then M sub S, right? So what does N equal to? Like what is N?
The group, I guess. Like,
Not the group.
Principal quantum.
It is. It's the energy. Yeah, it is the principal quantum number. It's not the group. It's the period. It's the row.
yeah,
typically.
yeah.
So, or just the energy level. And remember, since it's an energy level, N cannot equal to 0 because that's, you can't just be on a non-energy level. And then next we have L. Like what value could L be? Like what does it range from?
From 0 to 2.
To 2?
Well,
Remember,
I don't know
like,
about I don't know the F one. Sorry.
From 0 to n minus 1.
so 0 from n minus 1, and in some cases with like your Fs, so your little F orbitals, sometimes it can be to n minus 2 sometimes. It's not always the case, but it can be sometimes. I doubt you guys will be working with the F orbitals a lot, but just something to keep in mind. And then on to M's of L. What range does this could this value be?
From negative L to positive L.
Exactly. And then from there we have M's of S, which is like the spin. And what values could this be? I'll give you a hint. It's only 2 values. And
Positive half and negative half.
Yeah, we have like positive 1/2, negative 1/2. Exactly. Well, let me put like why is it not? There we go. Sorry. Yeah, positive 1/2 or negative 1/2, right? So let's take an example, right? So let's say I have my n is equal to 2, right? What are my possible ranges for L?
From the to fluorine.
Oh,
No, like
from 1 to 7.
Oh,
sorry, can you repeat that? Like, what's my possible ranges of L?
From 1 to 7.
I'm sorry, can you speak up a little bit? I can't seem to hear you.
It's from 1 to 7.
1 to 7. So remember, our L is based off n, which is it starts off at 0, and it ranges from 0 to whatever n minus 1 is.
on this one, isn't it 0 to 1?
Yeah, exactly. Which is because n, which is 2 minus 1, is just 1. So it'd just be 0 and 1. And so that's my possible ranges. So let's say we decide to look for an electron in 1, right? So let's, for definite, let's pick 1 here.
That's
And
a
so,
p shell.
Exactly, it's a p orbital. So going back to our, so that's why these L's are important. Like we narrowed down where we want to find an electron. So if n is energy level, and then L would be like subshell, like that's what the numbers would mean. So from 0, 1, 2, 3, since you said that 1 is P, what would 0 be?
The S.
And then what would 2 be?
D.
And then 3?
I'm guessing it's F.
Exactly. So these are like the possible shells. Whenever you see these numbers, this is what the orbital shells they're talking about. So since we're picking a definite 1 out of the possible values, let's go to M's of L. So what would be my M's of L in this case if L is equal to 1?
Well, we haven't picked. I don't know.
We have
we
picked
need to
1.
know what we're looking for that.
Right now we're just looking for, let's just say we're looking for like the last electron. That I just want you guys to get the idea.
It could be -1, 0, or 1.
Yeah, exactly. These are the possible ranges, right? And if you remember from your orbital box diagram, since this is a p orbital, So we have a 2p because we're on the second energy level. Here we have our 3 boxes, and we would assign the numbers, right? We would have -1, 0, and 1. That's why we have this range to correspond to the boxes, right?
Yeah.
So let's say, let's just make up a orientation here. Let's make up this orientation here, and let's focus on the last electron. So which of these electrons is the last electron in this orbital?
1.
The -1, right?
Yeah, it'd be -1, right? Because the way we count them, we start off with up arrows and then end with downward arrows to make them pairs. So this electron right here is our final electron. So we would make, so mLs would be -1. And now our ms, we know the possible values are +1/2 and -1/2. But which of these two is it if we're focusing on this electron?
-1/2.
Mm-hmm. Exactly, it'd be -1/2 since it's pointing downwards. So let me quickly fix this up. So this would be like technically the coordinate system for this electron, right? But let's say I want to focus on a different electron. Let's say I want to focus on this right one here. Which of these values would change if I'm focusing on this electron?
ml and ms.
Mm-hmm. And what would they change to?
ml to 1 and ms to +1/2.
Mm-hmm. Exactly, because it lands on the 1 box, and it's +1/2 because it's pointing upwards. Mm-hmm. So that's perfect, right? So let's see here. How do you know it's a p orbital? Because n is equal to, we look at L because the number that L has corresponds to a subshell. So if we look over to the right here, like this, right above this line. So if L is equal to 0, that electron's in the s orbital. If it's 1, it's in the p. If L is equal to 2, it's in p orbital, 3f, and then so forth, so on, right? So that's why L is important, because we start off just energy level, right? We start off with just the row it's in. And then we narrow it down to the orbital it's in. Because remember, they could have either both or all of them
In order to find all of them, you have to have L first.
Mm-hmm.
Okay.
Well, in order to find a specific electron, yes, because remember, these numbers right here, they can have a range, right? So we saw that it could range from either 0 to 1. That means it has an s orbital and a p orbital that we need to decide which electron we want to find in one of those orbitals. So here, let's do an example real quick. So let me quickly gather all this up.
I have a quick question on the last one. You know how L can go from 0 to n-1?
Yes.
How do we know it was 1 and not 0?
We just decided because we weren't working with a specific electron or an element. We just decided that way so I can show you guys that, we're kind of narrowing it down so you can know how to identify mLs and then ms. So,
okay.
And this time we are going to try to do a definite one. So let's find the last electron within, let's say, sulfur.
Okay, thank you.
You're welcome. So sulfur, what's the N of sulfur? Like what energy level is it on?
2.
Yeah, it's on the, no, it is not 2, because remember, energy level corresponds to the period it's in the row it's in.
I'm sorry, 3.
Yeah, 3, exactly. So since it's in 3, what are the possible ranges for its L?
0, 1.
0 and 1?
Well, yeah, 0, 1.
Those are its possible values, but remember that L is from 0 all the way to n-1. So if we take our n, our 3 minus 1, that gives us 2. So it ranges from 0 to 2. So we have 0, 1, and then 2, right? And so if we look at it on the periodic table, like what, because remember, what do these numbers associate with?
Subshells.
Subshells. So we know that 0 is S, 1 is P, and then 2 is D, right? And what the subshell is sulfur currently in if we're finding the last electron?
P.
So if we're looking for the last electron and sulfur is in the p orbital, our L has to equal to 1.
Yeah. Well, I say 0 and 1 because technically the only options until you go to the fourth shell.
Technically, but then I don't want to go into this to confuse you guys, but like it will have like an empty d orbital, but we don't count it because it's empty. But that kind of goes into bonding and back to like its geometry, but you guys don't have to worry about that yet. So yeah, so it would be like, so our L is for 1 since we're looking for the last electron. So now what will be my ranges from M to L's or M's of L's?
-1, 0, and 1.
Mm-hmm. So we know we had to plot these on here. So let's plot them onto our little thing. So if we know it's on the 3p, we put our little box here. So how many electrons does sulfur have in its 3p orbital? Just by looking at your periodic table.
4.
Mm-hmm. So if we count them up by 1, 2, 3, and 4. And which of these electrons is its last electron?
-1.
Mm-hmm. So, oops, sorry, let me move some stuff. Yeah, we have -1, 0, 1. It's in -1, right? But which of these two are they?
The -1.
Yes, it is in the -1. But which of these two electrons within -1 is the last
The
electron?
one on
But downwards.
Exactly, downwards.
-1.
So here's our last electron. And so that would mean that M's of L is -1. So now what will be my M's of S?
-1/2.
Well, what's positive or negative?
-1/2.
And why is that?
Because it's pointing down.
Exactly. So these would be our final quantum numbers for the last electron for sulfur, or ground state sulfur to be more specific. And then -1/2. So like you kind of write your answer, final answer like this, like a grid system, like in your parentheses. So let's do another example. So let's do another example here. Let's say we want to find the last electron for oxygen. And what would be the energy level of oxygen right now?
2.
And what would be the ranges of L if N is equal to 2?
0 and 1.
And since we're looking for the last electron, which we know that 0 is S and 1 is P. Where is oxygen located right now? In which orbital?
1.
So since L says, so now we're making L equal to 1 because that's what we're looking for. So now what would be my ranges for M's of L?
-1, 0, and 1.
Oh, the MS on the previous one was -1/2. Just so you know, Eva. And so we have -1, 0, and then +1. So here we have, so like this, so we have our little box here, which is in 2p. And we know that it has 4 electrons. So 1, 2, 3, 4. So just like sulfur, we see that it's the same thing. It's in a -1, right? So since it's pointing downward, we have our MS equaling to -1/2, right? So that's how you get the gist of quantum numbers. Do you guys have any like questions? Anything you guys are confused about? All right, I'll take that awkward silence as a no, and we can move on to the next module. So whoever was recording, can you like stop recording?
I think that was Corina.
Was it?
Oh, give me a sec.